Okay, so a tradition which started here several years ago is to have some speakers outside the standard format of the school. The idea was that people come from all over to Princeton and they would like to see some of the distinguished people here. So we have 3 special lectures on topics which are somewhat related to the school but a little bit outside the main focus of the school. So if you have any problem with that, the material that these talks will cover, particularly the talk today by Igor, this material will not be in the final exam. So it's really a great pleasure to introduce Igor Klebanov from our sister institution, which also co-sponsors this school. And he will be talking about the warped conifolds and their applications to cosmology.
Okay, thank you very much for the invitation. It's a real honor to be giving this special lecture. Now, those of you who read the abstract that was posted know not to expect some light entertainment. In fact, I tried to prune it a little bit, but still my task is rather formidable because I plan to somehow cover both some aspects of gauge string dualities, in particular ADS-CFT duality, and also some hopes for applying them to real world, which is, of course, somehow the ultimate goal of any theoretical physicist. So here is the title, and before I get into the conifolds, I just wanted to say a few words about ADS-CFT correspondence, which relates string theory to gauge theory in a rather convincing way. And the way people arrived at the ADS-CFT correspondence was to study objects called D-branes, which is short for Dirichlet branes, which are special hyperplanes in 9+1 dimensional space where open strings can end. So for example, if you have type 2B string theory, which in the bulk has only closed strings, these closed strings, when they touch a special D-brane location, can open up and live on them as open strings. So basically, these ends of open strings have Neumann boundary conditions along the branes and Dirichlet boundary conditions transverse to the branes, hence the title. And one of the reasons D-branes are so important is that they provide a new way of embedding gauge theory into string theory. In particular, if one studies the massless states of the open strings living on D-branes, one actually finds gauge theory. For example, a single Dirichlet 3 brane, which has 3 internal spatial and 1 time dimensions, just like this room, realizes U1 gauge theory with maximal supersymmetry, with 16 supercharges. And the further important fact is if one considers a stack of n coincident D-branes, Dirichlet 3 branes, then you actually find UN gauge theory in 3+1 dimensions, again with n equal 4 supersymmetry. So this has played an important role in many applications, but one sort of way to think about this large stack of branes is to also realize that these D-branes actually are expected to curve space in some way. And they produce a curved 10-dimensional metric. Here is the expression for this metric. Even if you're not proficient in metrics, you basically realize the following fact, that these D-branes have 6 dimensions transverse to them, and this is parameterized by this part of the transverse metric, just dr squared plus r squared d omega 5 squared, where d omega 5 squared is the metric on the 5 sphere surrounding the branes. And then there are 3+1 dimensions along the brane, and they're not totally decoupled. They are related by a so-called warp factor, whose form is 1 plus L to the 4 over R to the 4. And these type of warped product spaces will play a very important role in everything I have to say. So this is literally the metric produced by the stack of branes. And it has a peculiar property that when you go very near the branes to r equals 0 or very small r, this sphere actually will not shrink but just approach a constant size, because this factor becomes L squared over R squared, so R squared cancels out. And this is depicted by this kind of semi-infinite throat. So this throat clearly has a 5-sphere in it, and the remaining coordinates actually combine into a negatively curved space called anti-de Sitter 5. So far down this throat, you find ADS 5 crosses 5. And it turns out that the low energy limit, which decouples open strings from closed strings, kind of decouples this ADS 5 crosses 5 throat from the asymptotic 10-dimensional space. And this is basically the argument for the duality between n equal 4 super Young-Mills and the ADS 5 crosses 5 background. So basically, more generally, ADS-CFT duality relates various conformal gauge theories in 4 dimensions. So here I'm focusing just on the gauge theory in 4D case. There are other important and interesting cases, but this is the 4-dimensional case of our world. And this is dual to some 5-dimensional anti-de Sitter space times some 5D compact space, which in the simplest case is a sphere, but more generally can be something more involved. And there are many arguments for this duality. For example, the geometrical symmetry of ADS5, which is just a kind of hyperboloid, is SO2 comma 4, which is identical to the conformal group in 3+1 dimensions. And the special property of these type of hyperboloids is encoded in these Escher diagrams, where you see that if you assign the same size to these fishes, you see that as you get close to the boundary of this disk, there are many, many more fishes than in the interior. And in fact, the number of fishes kind of diverges near the boundary. This is encoded in the fact that there is a warp factor 1 over z squared, which blows up near the boundary of this 5-dimensional space. So this is probably many of you heard this, but I think it's important to realize that D-branes were kind of important in at least building the well-known cases of ADS-CFT. And now I want to move on to cases where you don't have maximal n equal 4 supersymmetry, but break it in some way. And a useful tool for this is so-called Cone-Brane Dualities. Maybe you've seen some old TV shows where there were cone heads or cone brains, but some of these pictures will show up later. Okay, so the idea is that rather than just stacking these branes just anywhere, you want to stack them on some special kind of Ricci flat cone. Of course, the most trivial cone is just flat space. This is a cone over a 5-sphere, but there are more general cones, of course. For example, you can mod out this flat space by some discrete group so that there is some finite opening angle. But there are more complicated spaces, and the Conifold actually is one of them, which I'll spend most of my time on. So if you imagine such a cone, it's easy to show that when you write the metric of the cone like this, the base of the cone is an Einstein space. Namely, for this space, the Ricci tensor is proportional to the metric, and the canonical normalization is to say that Rij is equal to 4Gij. And then when you play, you can play exactly the same game as was played on this transparency. Just replace d omega 5 squared by the metric on this base of the cone, and then at small r you get ADS 5 cross the base of this cone. So it gives you a kind of rather general set of ADS 5 cross something geometries, and then the flux created by the branes pierces this geometry, and you find the relation that the radius of this space to the 4th power is proportional to G string n. And G string n is the relevant coupling constant for this gauge theory. So when this radius is large in string units, this volume of y is just some number of order 1. So when when the ratio of L to the 4 to string scale to the 4, which is alpha prime squared, becomes very large, that means that the field theory is very strongly coupled. So this gives you a way of studying strongly coupled field theory using string theory on ADS 5 cross Y. But first we have to decide what field theory we're dealing with. And this is a kind of more difficult task. To construct this geometry, as we saw, was an easy task, but finding the field theory can be difficult. And the early papers on this, for example, by Kachur and Silverstein and others, were basically taking some field theories at stacking D-branes at orbifold singularities, namely R6 mod gamma. And then there was a very simple set of rules. You start with n equal 4 super Yang-Mills, make a certain projection, and get the field theory. But then there are somewhat more complicated cones, which are not locally 5-sphere. They're not just some kind of 5-sphere with points identified. And perhaps the simplest kind of example of that is the Conifold. The Conifold is a well-known space in string theory, because if you take a generic Calabi-Yau space and move around by changing its parameters, you rather generically find that locally these little conic points develop. So the space will not look truly like this, but you imagine this sharp conic point being glued into some complicated compact Calabi-Yau space. And locally, if you sort of scale the coordinates around this cone, you generically find the following equation in 4 complex variables. Just the sum of squares of these variables is equal to 0. And this was first demonstrated by Candelas and De La Osa back in the 80s, and they started studying the properties of this space. Now, this space is clearly a cone, because you can rescale all coordinates by the same number. And for historical reasons, the base of this cone is called T11. It was actually discovered by supergravity people even before the Conifold importance for strings was realized. It's a kind of coset space, but in a nutshell, the nice thing about it is that its metric can be written perfectly explicitly. What you do is you define two spheres, two two-dimensional spheres parameterized by the usual theta and phi coordinates, and have additional circle psi, which is kind of fibered over these two spheres. And this fibration is specified by this extra term in the metric mixing psi with the theta and phi coordinates. And these 1/9 and 1/6 numbers are determined from the condition that it's an Einstein metric, or one can just start with this constraint and really derive this by parameterizing z's in certain ways. Now, in this parameterization, it's not so obvious what the symmetries of the space are, but here some symmetries are truly obvious. For example, you can just rotate the z's into themselves, and this gives you an SO4 symmetry, just rotating the z's, which can be broken into SU2 cross SU2. The significance of this will be realized soon. And then you can rotate all the z's by a certain U1 angle, and this turns out to be the R symmetry in the gauge theory. Another important thing is that the topology of this space is that of a 2-sphere times a 3-sphere. And this is quite different from the 5-sphere that we had in the original case, and this actually will allow us to play some additional interesting games with the space. So now the question is, what happens when you stack branes at the point z equals 0? What sort of gauge theory do you get at low energies? And in a nutshell, there is a kind of prescription for deriving this theory. One can decompose these z variables into some auxiliary variables a and b, such that if you write first z variables as a 2x2 matrix, you can automatically implement the constraint that z equals 0, which is same as the original constraint, by writing this entry as A1B1, this one as A1B2, and so on. Then the constraint that the determinant is 0 is automatically implemented, but there is some redundancy in these A and B variables. And, but some symmetries become manifest. You get SU2 symmetry rotating the A's into themselves, another SU2 rotating the B's, and then the R symmetry rotates them by certain angles. And then to remove some of this redundancy, you can fix the condition that sum of absolute values of A squared equals sum of absolute value of B squared. And this is from the, if you think of these as certain charged fields, this looks like a D-flatness condition in a gauge theory, in a supersymmetric gauge theory. So basically, to really think of it as a D-flatness condition, you actually basically postulate that the IR gauge theory on a single D3 brane has gauge group U1 cross U1, and the charges of A's and B's, so one of these U1s is just neutral, and the other U1 has charges plus, plus, minus, minus. Then the D-flatness condition literally becomes this, so everything hangs together. So essentially, these A and B variables are promoted to chiral superfields, matter fields in this n=1 supersymmetric gauge theory. And the n=1 supersymmetry follows from the fact that the Calabi-Yau typically breaks supersymmetry to one quarter of the original maximal supersymmetry. Okay, then as we proceed to a stack of n branes, there is the usual guess that that basically U1s gets replaced by UNs for the reason that there are now n species of string, n squared species of strings. And then these chiral superfields now sit in bifundamental representations, namely A1 and A2 are in the anti-fundamental with respect to first SUN and fundamental with respect to second, and B1 and B2 are conjugate. Then the condition of anomaly cancellation, so that U1 R symmetry is non-anomalous, uniquely fixes that the R charge of each field is 1/2. And this is, as you probably know, the dimension of the field is 3/2 times the R charge. So these fields don't have their free dimensions. Their dimensions are actually 3/4 rather than 1. And this is a typical situation in supersymmetric QCD in the Seiberg conformal window, that fields require these type of anomalous dimensions. And this theory is actually very similar to supersymmetric gauge theory with NF equal to 2NC, which I think you'll hear about later in the school, these type of conformal window theories. And then one also has to add a marginal, exactly marginal superpotential, the one that doesn't spoil conformal invariance. That has to have R charge 2, and that just fits exactly with it being quartic. So, this quartic expression basically does not violate the conformal symmetry of the theory, so it satisfies all the constraints of conformal invariance. And the proposal made by Ed Witten and me some time ago is that this is the theory dual to ADS5 cross T11. And one can make various checks of this proposal, but we want to kind of make the theory as interesting as possible. So we want to now break conformal invariance. We don't want to just stop with exactly conformal theory. And when one breaks conformal invariance on the geometric side, there is an interesting fact that just thinking about the conifold, at the conifold singularity, as you know, the base of the conifold is a 2-sphere times a 3-sphere, and at the tip of the cone, both of them shrink to 0 size. And in fact, so you would think that there are two possible smoothings of this singularity. In one of them, the 3-sphere remains while the 2-sphere smoothly shrinks. In the other one, the 2-sphere remains as the 3-sphere smoothly shrinks. And these are indeed two possible well-known supersymmetric sort of smoothings of the conifold. One is called, and this is the technical term, the deformation. it just replaces the constraint by introducing a parameter epsilon squared on the right-hand side. Then it's not hard to see that at the tip of this space, you just have a 3-sphere where all the z's are real, and you just have a 3-sphere of radius epsilon, basically. And then there is a small, so-called small resolution where you still keep 0 on this side, but modify the constraint on the a and b variables to now, in this equation, add some parameter u on the right-hand side, and this will play the role of the radius of the 2-sphere. So we want to, the goal is to somehow modify the theory so that it becomes confining in the infrared, because we want to get as close as possible to QCD, which is a confining gauge theory. You may be wondering, where is cosmology in all of this? Well, that will come in the last 10 minutes. For now, we're just playing with these geometries of these spaces and trying to see how these geometries are reflected in the gauge theory. So let's make the first simple attempt to introduce a scale into the theory. So I have this theory with A and B fields, and when it's conformal, the A and B have no classical values, right? So one way to introduce a scale is to just give some classical values to one of these fields, for example. That introduces some dimensionful parameter, and then we want to know what happens to this theory in the infrared. Well, it turns out that when you introduce, just give a VEV to one of these chiral superfields, the relevant geometry becomes this resolved conifold, but with a certain complicated kind of warping. So we get something we call warped resolved conifold. So basically in the gauge theory, the resolution is achieved just by giving vacuum expectation values to the chiral superfields. The reason this is suggested is because clearly, once you start playing with the classical values of these A's and B's, there will no longer be a constraint that this is equal to 0. Instead, it will be equal to some non-zero number. And that's the space that we're dealing with. OK, so for example, we can give, say, a VEV to only one of the 4 superfields, say B2, make it just the identity matrix, and by an identity matrix. And then the claim is, and this was worked out actually this January by my student Arvind Murugan and me, the claim is that there is a very specific warped resolved conifold geometry which is dual to the space with this, dual to this gauge theory with the VEV. So one thing that's also helpful is that there is an explicitly known, very explicit metric on this resolved conifold. Here is the metric, so it's just written down in terms of elementary functions. You basically see that at r equals 0, this particular 2-sphere, the theta 2 phi 2 sphere, no longer shrinks to 0 size, but keeps radius u, which we knew from other considerations, while the remaining 3 directions basically shrink to 0. And then what happens is that you take this space, and the stack of D3 branes somehow comes back, and it sits at some point in the space, for example, and you just have to pick the relevant point where it sits. And this stack of branes acts as a kind of source for the warp factor. The warp factor is a harmonic function, namely it satisfies del squared h equals 0, but there is a delta function source at the location of the stack of D branes. So somehow, while in ADS 5 crosses 5, the stack of D branes was not obviously there, it kind of comes back, sits at some point, and sources this warping. And then one can actually solve in simple cases for this Green's function exactly in a kind of multipole expansion. Here, it depends on only 2 coordinates, theta 2 and r, and has a very simple expansion in terms of known special functions. These are the Legendre polynomials. These are some hypergeometric functions. And then one can check that in this sum, everything works out just right to have a kind of pole of this warp factor at the location of branes. And far away, this warp factor approaches the 1 over r to the 4, which gives you ADS 5 cross T11. So the interesting thing about this is that this kind of interpolates between ADS 5 cross T11 at large R in the UV and ADS 5 crosses 5 somewhere another throat like this going off in the small R region. So this really describes an actual non-conformal theory which flows from this SUN cross SUN gauge theory just down to SUN n equal 4 super Young mills in the infrared. So even though we've broken conformal invariance, far in the infrared we're not finding confinement. We're instead finding another conformal field theory, which is a rather typical situation, but it's somewhat satisfying. At least we have some control over solutions that flow. Nevertheless, it's not somehow, even though we've broken conformal invariance, we didn't end up with confinement. So what should we do to get confinement out of this game? Well, it turns out that while the resolved conifold doesn't work, the deformed conifold actually does give confinement. And one way to see what confinement corresponds to quite generally in ADS-CFT is to study the quark-antiquark potential. This is accomplished by putting some quark and antiquark at the boundary of ADS space, namely at z equals 0 in these coordinates, and connecting them by a string that somehow penetrates into the interior. Now, if the quark and antiquark are close together, a calculation that was done by Juan Maldacena showed that the potential is coulombic in that regime. So very near the boundary, the potential will be coulombic. But suppose the space somehow gets deformed a lot and comes to an end at some finite z, then what can happen is that as you move the quark and antiquark apart, the string wants to go to the end of space and just elongates at this minimal coordinate where it retains its tension. And this is just the phenomenon of confinement because the quark, in these circumstances, the QQ bar potential will be linear at large separations just because of the string kind of elongating at this location. So this is kind of a cartoon of what happens. And there are some models where it really does happen honestly, basically in 10-dimensional language. And one of them is based on a deformed conifold. We call it warp deformed conifold. So as I showed, to create resolved conifold, one has to do something relatively simple. But to deform the conifold, one needs to do something a bit more complicated. In addition to the n D3 branes at the tip of the conifold, one adds also some number of Dirichlet 5 branes, which are wrapping a very small 2-sphere at the tip of the conifold, but still have 3+1 additional dimensions. So this assembly of branes actually creates the kind of theory we want, or at least works for the confining purposes. And then the geometry that this assembly of branes creates is the warp deformed conifold. So now this ds6 squared describes the metric on this deformed conifold space. And this warp factor can be solved for explicitly, and it exhibits this kind of property that we want to have confinement. So you can ask, where did this epsilon come from? Well, it turns out that when you add these D5 branes, they create some amount of flux through this 3-dimensional sphere. And this flux doesn't want the sphere to shrink to 0 size. So if you just assume that there is a finite 3-sphere, then the solution becomes perfectly non-singular. Well, when epsilon formal is forced to 0, there is no smooth and non-singular solution. So this is the way in which somehow the string theory is telling us to introduce this parameter. And this parameter actually, from the gauge theory point of view, will have the interpretation of the infrared confining scale, as I'll explain in a second. So the warp factor can be, then one needs to go to a certain series of steps to obtain the exact solution. But the most complicated thing about the solution is actually the warp factor, which is an integral over certain products of hyperbolic functions. And this warp factor, if you plot it, it has the following let me just show you. This warp factor is perfectly monotonic. It starts at 0 and then monotonically decreases at large R, and here starts resembling very much the ADS 5 cross T11 modulo logarithmic corrections. But if you didn't introduce this deformation, then everything would be okay at large R, but at small r, the warp factor would kind of stop being monotonic, dip down to 0, and at this point would exhibit a so-called naked singularity, very undesirable singularity where the whole transverse space shrinks to 0 size. So it's really in the effort to avoid this unphysical behavior at small r that we must introduce deformation and then have this perfectly monotonic warp factor. Okay, and this is just the plot of this function that I was exhibiting here. And now the string tension is just basically 1 over square root of h. So you see that the string tension is actually minimized at t equals 0. So if you drop a string, it will naturally fall to this bottom of this conifold, and this is literally the picture that we wanted to have. We wanted to have a string attracted to this bottom of space, and this is how the confinement happens. So it's really a very simple language how to see confinement in this particular set of metrics. Another nice thing is that if one takes G string M to be large in units of alpha prime, then the 3-sphere is large and the whole solution is reliable. So you get a kind of solution of a certain confining gauge theory, although it's not QCD, but as I will argue, it's a kind of distant relative of n equal 1 supersymmetric gluodynamics. In particular, there is some, in principle, well-defined deformation, which we don't know how to do, but which would take us to n equal 1 gluodynamics. Okay, so as I mentioned, there is some kind of dynamical scale generation in this theory, and this really comes from the fact that there are logarithms in the large R or ultraviolet region. In this region, the solution is more simply written down. There are no hyperbolic functions. There are just logarithms and powers. And you see that, for example, a certain field which pierces the 2-sphere grows logarithmically in the UV, and this is related to the logarithmic flow of a certain combination of the 2-gauge couplings. We have SUN cross SUN, and if we look at 1 over G1 squared minus 1 over G2 squared, it's precisely related to this B2, which varies logarithmically. And moreover, one can even compare the coefficients between field theory, Schiffmann-Weinstein beta functions, which one can easily write down for this theory, and this what the gravity is telling us, and we find exactly the same coefficient, provided that in the UV, the anomalous dimension of these operators is dictated by their conformal R charge, namely gamma is -0.5. Then you see that you will get you get a factor of 6 here, which precisely agrees with this gauge string duality argument. So you see that there are basically logs, and whenever there are logs, you can't just write log R. There has to be R over something, and this something will eventually transmute into some dynamical infrared scale, and this something is really what's becoming this epsilon. It's related to this epsilon. Okay. The other very peculiar thing is that the 5-form flux, which used to measure the number n of flux units, is itself kind of varying logarithmically. And what could be the interpretation of that? Well, as you probably know or will hear later in the school, Seiberg duality connects theories with different numbers of colors. So the number of colors is somehow not sacred in these supersymmetric n equal 1 supersymmetric gauge theories. And in fact, one can follow a so-called duality cascade of these SUKM cross SUK -1 M theories, where you repeatedly apply Seiberg duality and see how this number of colors is dynamically gets somehow reduced as you flow to towards the infrared. And to make it a bit, so this is a rather sophisticated plot from a recent review by Matt Strassler, but it basically shows how this theory goes through a series of downward steps in this K, which measures the rank of the gauge group. To make it a bit more explicit, if you look at the, say, bigger gauge group, SUKM, you see that effectively these A and B fields amount to 2Km minus 2M flavors. Okay? And the Seiberg duality maps SU and C to SU and F minus NC, which turns out to be SUK minus 2M. So after you perform this duality, you basically see that SUKM cross SUK minus 1M gets mapped to SUK minus 1M cross SUK minus 2M, and so it goes. So it undergoes this kind of quasi-periodic RG flow until K drops to something of order 1 in the infrared. And then some more interesting things happen. But roughly speaking, in this fashion, you could flow qualitatively to just SUM. So K can just become 1. And then far in the infrared, you recover the n equal 1 supersymmetric gluodynamics, which is a very interesting theory and would be very useful to solve. In particular, it's a confining theory whose spectrum is not known yet, and so on. So this I already showed. Basically, the ADS warp factor giving conformal behavior, there string tension just vanishes because string tension is 1 over root h, and warp factor blows up at small r. So this theory never generates any string tension. This theory is a little bit sick, but should be interpreted somehow as just the UV limit. And this theory is perfectly healthy and actually has confinement, has finite string tension. And in fact, qualitatively, this type of theory is rather similar to QCD. I actually had a senior thesis student this past spring plot numerically the quark-antiquark potential for precisely this metric. And one thing you know is that at very short distances, it's approximately 1 over r. And at long distances, it's going to go as r, and somehow there is a smooth interpolation between the two. And if you look at some lattice QCD results, which took many hours of computer time to measure, they look sort of similar. I mean, there is at large r, there is clearly a linear potential, and here there is a Coulombic potential. This, of course, is very simple classical kind of calculation related to these string shapes. It's not QCD, but it's at least a model field theory where we can establish confinement, a model 3+1 dimensional gauge theory. Okay, so this, and one can compute various other observables. I will not go into the more hairy stuff related to the baryonic branch of this theory and so on, but just limit myself to a few remarks. So clearly we find some regime where there is an exact solution of this theory via geometry, via string theory, and at least this could be a playground for testing some ideas about strongly coupled gauge theory. In particular, one can compute the spectra of bound states like Lubel spectra, and some calculations are already available. Essentially, the way one computes them is by studying fluctuations that take place very near the tip of this conifold, where the space just ends smoothly. So there are some fluctuations with wave functions localized in this region. And they're tough to calculate because there are many fluxes and so on, but these calculations have already been ongoing for years, and there are many interesting results. So at least this is a kind of model of 4D confinement. But if one is more ambitious, one could ask, could there be applications of these models to new physics somehow? Because as I mentioned, from string point of view, these conifold spaces are rather generic. And if one turns on the right combination of fluxes, then these conifolds get warped and provide for you this type of way of generating a very low scale relative to the string scale. Okay, so then basically the second part of my talk will be about these type of applications. These are applications where you don't just have a non-compact deformed conifold, but you imagine that it's really glued into some kind of compact Calabi-Yau space. So you imagine that there is a compact Calabi-Yau with some kind of little conifold singularity, which then gets somehow warped by some appropriate number of flux units and turns into a so-called warped throat. And in the region of this warped throat, what happens is that the warp factor is very well approximated by the formula that I showed you. And in particular, the scale of string tension is much, much lower here than it is in the bulk of space. It can be lowered by many orders of magnitude by appropriately choosing this. So it can give you, for example, strings whose tension is much, much lower than the Planckian string tension. And this is one application to get somehow cosmic strings into your scenario. But there is a perhaps somewhat less obvious application just to inflationary universe. So that's what I want to discuss. So as you probably heard from many colloquia, there is increasing confidence in the inflationary universe idea. Basically the idea that very early on in the history, for a tiny, tiny fraction of a second, there was a de Sitter phase where the universe explosively inflated with a cosmological constant which was on the order of, I don't know, 10 to the 14 GeV all to the fourth, or that order of magnitude. And then the predictions for the observed CMB spectrum, that here is a picture from the more recent plot, including polarization directions. That matches very well with rather generic predictions of the inflationary scenario. But there are nevertheless problems in the sense that there is somehow no convincing fundamental theory underlying this type of effective field theory one writes down for inflation. In particular, if one wants to write down a so-called slow roll model for inflation where the potential is not too steep, it's apparently very hard to do. And some of what I will say will kind of relate to this. But one of the more recent tools for constructing inflationary models once again have to do with D-branes. In particular, Dvalli and Tai proposed a very simple setup where you say take an anti-D3 brane somewhere and the D3 brane parallel to it. They somehow weakly attract with some potential, and the rolling of then the distance between them plays the role of the inflaton. The evolution of this inflaton is just D-branes rolling towards each other. And what if that gives us an acceptable model? Well, unfortunately, just D-brane, anti-brane, and flat space, one can quite easily show it does not give enough E-folds of inflation. It doesn't give a working inflationary model. And then these authors, Kachru, Kalash, Linde, Maldacena, McAllister, and Trivedi, had the idea to kind of provide a variation on this idea, which is put the D-brane and anti-brane somewhere near the bottom of this type of warped throat, like the warped deformed conifold. Then there are some really real advantages. First of all, the anti-D3 brane is naturally attracted to the bottom of the throat, where its tension becomes much, much smaller than the tension out here. And that provides a rather reduced kind of uplifting mechanism, which, you know, if you're familiar with the KKLT scenario, that has a negative vacuum energy, which is supposed to be cured by uplifting through this anti-D3 brane. So that's a first step. So it naturally falls and stabilizes at the bottom of the throat. And then one adds a mobile D3 brane. The force between the two actually gets reduced by the same warping mechanism that reduces the tension. So everything gets warped down and the potential gets much less steep. And that was pointed out in this paper. And since then, many people got excited and are trying to really use this type of model of D-brane inflation. Another consequence of this idea is cosmic strings, which is already something I alluded to. It turns out what rather naturally happens is when these D-brane and anti-D-brane annihilate, during this process of annihilation, you tend to form cosmic strings. And in this picture, these cosmic strings are nothing mysterious. They're just the same strings that one dealt with when measuring this string tension. Namely, it's just the fundamental strings whose tension, who live in this region at the bottom of the conifold, and their tension gets reduced by this, again, by this very large warp factor. But you're not limited to these ordinary strings. There are also D strings and various bound states of fundamental and D strings. So the warp factor from the point of view of this compactification is exponentially small. Basically, if there are k cascade steps taking place in this throughout gauge theory, this reduction in tension is by an exponential factor, which can be made sufficiently basically as small as you want by increasing k. So enough flux will warp it down. And this makes it not hard to attain the tension of less than 10 to the minus 7 in Planck units, which is more or less the present experimental bound. Without this warping, if you just have an unwarped string, it would be far too tense. It would be something of order 1 here and would not work. But in this type of models, the same string that from the gauge theory point of view is just the confining string or electric flux tube does the job. And the D strings, they're a bit more subtle. They're dual to certain solitonic strings in the gauge theory. They also do the job. So one has an array of interesting cosmic string possibilities, and recently Polchinski and collaborators have been exploring the applications of these ideas of strings at the bottom of warp throat for cosmic string networks. Okay, but coming back to the sort of initial inflation idea, the question is this potential really flat enough to produce somehow enough inflation, because the field has to stay at the top sort of for long enough time to produce so-called enough E-folds. And this turns out to be a very, very subtle question, because generically, when one actually puts in effects of compactification, one arrives at, one basically spoils the flatness. And this was pointed out already in the KKLMMT paper. The problem is that typical compactification effect, like a D7 brane that lives somewhere, basically I can't go into sufficient detail here, but it turns out that just the KKLT moduli stabilization mechanism, which stabilizes this volume modulus of the compact space rho, introduces some dependence of the potential on the D3 brane coordinate, which basically spoils the flatness. So the only hope is to balance this against some other effect. So we've been working for now over a year on a particular model which is calculable. Namely, one introduces some D7 brane which sits far down the throat, and it turns out that the D3 and D7 branes do interact with some appropriate potential which is computable. Essentially, the superpotential is modified to some constant plus some function of D3 brane coordinates times e to the minus a rho. And this function actually is extremely simple. It turns out that the way it arises is like this. If you think about the wrapped D7 branes, there is some kind of gauge theory living on them. This gauge theory has some infrared scale that it generates. So it generates the infrared superpotential. This D3 brane is like a flavor in this theory. So the dependence on the mass of this flavor is essentially responsible for dependence of this prefactor on D-brane coordinates. So So this is some technical details of the computation. One essentially needs to compute the tiny perturbation to the warp factor introduced by the D3 and integrate it over the force cycle that is wrapped by the D7 brane. And this is somewhat complicated to do, but the result is amazingly simple. Namely, if you specify the D7 brane embedding by some holomorphic equation f of z1, z2, z3 equals 0, then this prefactor is just the same function to the power 1 over n, where n is the number of branes. So there is a very simple kind of cookbook prescription that emerged. Namely, you take this holomorphic function, and this function, the raised to the 1 over nth power, is literally what needs to be plugged into this previously somewhat mysterious factor a. And then one can just calculate. To construct a detailed model, one can just calculate, because in n equal 1 supergravity, there is a formula for the F-term potential, which involves the superpotential and the Kähler potential. And now de Wolf and Giddings provided a prescription for how to compute the Kähler potential. It's a log of a certain mixture of the volume modulus and a function that depends on the positions of the branes, which is nothing but the Conifold Kähler potential. So all of this is known. One can just compute. So now there are 4 complex coordinates, rho, the volume modulus, and 3 D-brane positions. One can derive a formula by computing various scalar metrics and inverting them. One can derive some formula for the F-term potential, and one sees that the previous piece that gave rise to a steep potential has some extra term which hopefully can cancel it off. So there is the old troublesome term, and then there is delta VF, which comes from the dependence of W on these D-brane coordinates. So what we decided, and then there is, so typically there are basically Hubble scale corrections to the inflaton mass or inflaton potential, which make fine-tuning really necessary. But we want to somehow make sure that there is some kind of fine-tuning that can be done. So we studied a very simple embedding of D7 branes due to Cooper-Stein, who proposed just the equation Z1 equal mu, namely the positions of the D7 brane in this conifold is just specified by Z1 equal mu. Then you can just plug this, so then this f of z is just z1 minus mu, very simple linear function. One plugs it into this formula here and starts experimenting with various parameters. And one finds that generically the total potential has a kind of maximum and a minimum, and basically is not suitable for inflation. But there is a kind of fine-tuning that creates an inflection point. So if you start a field somewhere here, it somehow starts accelerating here, and somewhere down here it moves so fast that the inflation doesn't proceed anymore. If the field moves too fast, the inflation ends. And then you basically, so you have this very delicate situation where the field moves near this inflection point. These type of models have been considered before. They're certainly not very pretty models, but this is basically the sort of model that you arrive in this throughout inflation. One peculiar thing is that the spectral index, as you know, if the spectral index is less than 1, then there is sort of one sign of shift of the spectrum. If it's greater, then there is another sign. And here, even this is not determinate. So one can get either red shift or blue shift, depending on precisely where the inflation ends. So it's a very delicate scenario, and that's why we wrote a paper calling it a delicate universe. I'm not sure the referee will like this title, but basically this gives you some idea of how difficult it is to actually construct a kind of top-down models of inflation. That if one starts with this throat idea, which I think is a very sensible idea, one needs to plow through a lot of calculations. And even after that, you see that some really delicate cancellations are needed to provide models which have enough e-folds of inflation. So it's actually pretty remarkable how many ingredients this type of construction has. Of course, nobody has any confidence that this is how nature chose to realize inflation. But I think the starting point, at least, is rather natural from the stringy point of view. And I think it makes sense to pursue the variants of these types of models just to see if they can be simplified or made more natural. So let me conclude. Basically, I kind of started the talk in one place and ended in a rather different place. And it's nice that these two different places are connected, because on one hand, the starting point was just D-branes on cones and how they lead to dualities between strings and gauge theories. And the crucial point was the existence of these large warp factors, which vary significantly from one place to another. And then we saw that these warp factors can somehow stabilize and be monotonic, producing confinement. So confinement is a very natural phenomenon from the point of view of gauge string duality. And moreover, these models, this I didn't have time to cover in great detail, but they also exhibit chiral symmetry breaking, quantum deformation of moduli space, and other very interesting effects. But then if one applies this idea of large variation of warp factor to actual compact spaces, one arrives at a pretty generic possibility of warp throats that are glued into compact Calabi-Yau space. And this we saw rather naturally leads to low tension cosmic strings and to a possibility of rolling D3 branes and inflation. These models are complicated, no question about them, and the calculation of non-perturbative corrections to the inflaton potential are very important in determining whether these models actually work and whether they can be fine-tuned to produce low roll inflation. Okay, thank you for your attention. Yes. Yeah.
Can you quantify the amount of fine-tuning?
We haven't done so yet. I mean, it's ideally what one would need to do is to have a really good model for this picture, where you really start with a full embedding of this Conifold into Calabi-Yau. If one can, that would be the ideal thing. Because then you have the elementary fluxes to work with rather than just some derived parameters. Otherwise, one just needs to somehow look at, for example, what you can see is that, for example, near this point, there is both a lambda, phi cube term and phi term. And you can quantify the ratio between these two terms that produces enough e-folds. But these are not elementary parameters in some sense. So I know that this is the question that when I was at CERN a couple of weeks ago, people were very interested in that. So maybe there is some way to do it, but we haven't done it yet. The main new thing about this construction is that before people were just using an effective model where they said, okay, there is some phi squared potential at small phi. So this is the bottom of the throat. And they just assumed the cancellation of the phi squared term, which provided really flat potential all over here. What we find is basically these non-perturbative effects don't cancel phi squared. They just add a term with another phi dependence, like phi to the 3/2. So the best one can do is not to cancel the phi squared, but to create this inflection point. So this is a little bit worse than what a somehow naive analysis that people used before indicated. But I'm not, and it seems somewhat more fine-tuned, but I'm not But still, it's not a totally pessimistic story either, because there is this possibility. I would say that if you are a very generic landscapist, you would say, let me just assume some wiggly potential in this road, and then by some amount of fine-tuning, you can flatten various parts of it. And this is essentially what this is doing. So yeah, indeed, it's something that needs to be understood a bit better. One could also maybe create more features of this potential, which could be phenomenologically useful. Any more questions about any part of the talk? Yes?
Do you take account of the back reaction of the D-brane on the Untitled Chapter? Or you treat it approximation?
Well, that's essentially the way the calculation of this non-perturbative effect proceeds is literally through that. Because what happens is that, you see, if you ignore the back reaction of D3-brane, then it doesn't matter where it sits. Then you would conclude that this prefactor A is just independent of the D-brane position. What we in practice do is we compute the warp factor dependence on the position of the brane. Like when it moves slightly, the warp factor deforms slightly. When the warp factor deforms, the 1 over g squared, namely the coupling constant on the D7 branes, changes slightly because it's given by e to the minus the warped volume, the integral of the warp factor over this 4 cycle. So that's literally what we compute. We compute this back reaction on this g, and that gives us a very, very simple answer, just the holomorphic function of specifying the 4 cycle to the 1 over nth power. So in that sense, we certainly put in some of the back reaction. Without it, we would not include this somehow in non-perturbative interaction between the... Yes?
What sorts of things have been said about the n+1 dual, that confined and so on, using the ACFT value?
Well, I probably wisely removed some of the stuff that has to do with the infrared properties of this theory, because I just wouldn't have time, and it's also a particularly obscure subject. But essentially what happens is if you go back to the infrared theory, so when we consider this cascade, it eventually arrives at SU2M cross SUM theory. And there a really fascinating thing happens, because as far as SU2M goes, this theory has an F equal NC. And as Nati showed, in that case, there is a kind of baryonic branch that can develop, where certain baryonic operators, like when an F equal NC, you can antisymmetrize NC squarks. And it turns out that these baryons really have condensates literally in this solution. And moreover, one can construct a family of solutions where these condensates vary along the baryonic branch. They happen to be more complicated than the simple warp-deformed conifold, but now have been studied quite a bit. So in reality, you don't just have one confining theory, you have a kind of whole family of confining theories that can be solved by this mechanism. So that's one very interesting thing that we've been working on some in the last few years. But another point is that when you send G string M to be small, the spacing between these cascade steps becomes large. And then there is an argument that this theory will really become closer and closer to just n equal 1 super Yang-Mills. However, then the supergravity limit is no longer valid. So by computing, say, the spectrum of this theory, you're computing something in the kind of, you have this G string M, you can compute it reliably on one end, but you want to go all the way to the other end, and that's where it's n equal 1 super Yang-Mills. So, but still, it's interesting to compute it on this end, just in case some qualitative features would be the same and so on. So that's another thing that people are working on.
Okay, so let's thank Igor again.
Thank you. Is it okay?